the other side of the class. We'll see what we find out. And so I'm going to kind of tilt this at different angles. We'll see what we see. See if you notice anything? Anything interesting?
I saw a black line in this angle, nothing here in this.
Okay. So actually, you might notice that if you look at it at a specific angle, maybe you see nothing. It looks like it's clear, no crack, right?
Yeah.
Then you tilt it, then you start to see some different colors. You see the different colors? Two colors in particular, right?
White and black.
Yeah, so it's just some black and white. So look at the black and white lines. You see them? Okay. Do you want a sort of broken phone they can look at? Any other unfortunate souls? Okay, so we kind of saw at certain angles, we saw kind of a white line, and then at other angles, we saw kind of a black, dark line, just like right here. So here, maybe you can take a look at this. So I think it was around this angle. Do you see a dark line? You see it? Okay. So you do see it. Okay, good. So what we basically have is this. We've got glass. We'll call it glass. It's kind of like a plastic kind of glass. We have glass, and then in between we have some air, right? What does this remind us of? Yeah, the thin films. Yeah. Okay. So what's basically happening is at different angles, the thickness of this air film changes slightly because you have a little more air between your light source and your eye. So if you're looking straight down on it, maybe you don't notice anything because it's coming straight up. You don't see any of the thin film interference effects because you're basically looking at a crack. You don't really get that thin film effect. But what happens is if you look at basically a side view of this, basically here's your glass. So this is the glass. Here's the air, and here's the glass again. If you look at different angles, what you get... Hello, Richard.
Hi,
Richard's here. Now we can really start class.
Sorry, I'm sorry.
You were spelling time. Go ahead. It's fine. So what happens is at different angles, what happens is you're basically... Your line of sight is like this. Here, let me just find a different color. They have different colors. No? Oh, here we go. That's what I'm talking about. Okay. Maybe use a red one or purple one. So this is your line of sight here. Based on your angle, your essentially the thickness. So actually, let me draw this a little differently because you're actually kind of looking through a different part of the glass too. You're kind of looking through. You're cutting through part of this glass and part of the other glass. So it's kind of like this. This is like your line of sight, right? Like this. So at different angles, what you get is you're basically getting a different distance between this glass and that glass, because the glass is a certain thickness as well, but then so does this little film here. So the different angles, you might get a certain path difference here that produces constructive interference, which would give you a bright spot, right? And for other angles, maybe you would get an angle. Maybe you get a path difference here that produces destructive interference, and that's where we see that dark fringe. So what we're basically seeing here is we're seeing thin film interference at work, right? It's a real demonstration we can show. So yeah, kind of interesting, right? Interesting stuff. It's unfortunate that I had to break my phone's cover to realize that, but I guess there's always a bright side to everything, right? So just wanted to share that with you really quick. Also, a quick review from optics, because you will have to remember that at some point. Yeah, you can't just forget everything we learned before the break, unfortunately. All right. So the first thing we want to do today is we're going to take a quick look at the homework. Now, the first two problems shouldn't have been too bad. They should have been pretty basic and straightforward. But the last two, we didn't exactly talk about those topics, so I'll try to briefly explain them, but I'll probably also briefly talk about the relativistic momentum and the relativistic energy, just to kind of fill us in. So for 16 and 28, just give yourself full credit if you attempted it. If you didn't get it quite correct, that's fine. We didn't talk about it yet. So I expected to get through all that stuff by the end of yesterday, but we had a little too much fun with the relativity, which is a good thing. So no worries. Yes?
Did you give us back the, like...
Oh, yeah. The grading sheet. The homework sheets?
Yeah, I think we did that to you last term.
I think I might still have them. I think they're probably in my office somewhere. So yeah, I'll definitely get those back to you. So I guess for now, just make a quick note in next to your homework, and then I'll definitely get that back to you on Thursday. Yeah, thanks for reminding me. Okay. So I forget something before the break too sometimes, as you can see. Okay. All right, so let's take a look at the first two. So for number 7, so number 7 is basically just a length contraction problem. So remember from yesterday, the L value is always less than the L naught value. So we're using 25 light years for L and 85 light years for L naught. So when we plug these in and solve for the velocity, we should get a velocity of 0.956 c, which is actually the fastest velocity we've seen so far in relativity, at least in this chapter. And then what we're looking for is the actual time that it would take to make that trip. And so you divide your distance by your velocity. T equals d over v, and that gives us a time of 26 years. So luckily we didn't actually have to convert any time units here, because the c's cancel out, so we just know that our time is in terms of years. Okay. Any questions on the first one? Okay. Here's number 12. Number 12 has 4 different parts. So the first part is asking, let me pull this up here. All right, this is number 12. Okay. So you have a star that's 10 light years away, and they want to know how long would it take a spacecraft traveling 0.96 c on Earth, as observers on Earth or on the spacecraft. So that's probably in part B. So the Earth time is simply the L naught. Remember, L naught is the Earth time. It's the Earth time divided by the velocity of the spaceship. So remember, the velocity is the perceived velocity is the same for the Earth and for the spacecraft. It's the time and the distance that are different. So when we use this formula, we divide our 10.6 light year L naught distance by 0.96 c, which gives us 11.0 years as a time value. So since we're dividing light years by something in terms of the speed of light, what that gives us, basically a light year is the amount of time that it takes light to go in 1 year, right? It's the distance that it goes in 1 year. So if we have distance in 1 year divided by the speed of light, that just gives us the amount of years. So if you had 1 light year up here and divided by c, for example, then your answer would be 1 year. Does that make sense? Okay. So that's the first one. The second one, we have to find the dilated time for the spacecraft. So we're going to use 11 years from part A as our t value, our delta t, and then for t naught, for delta t naught, that's what we're looking for. So luckily here we can just plug in 0.960 for the v squared over c squared, and then square that, because the c squareds cancel on top and bottom,
So it's actually really convenient to express velocities in terms of c. Like what percentage of c is it? Because it's easier to plug into the formula. If you had it in meters per second, it would take you a little more time to calculate what that would be. So what we get here is a delta T naught of 3.09 years. All right, now part C. Part C says to the spacecraft observing the distance to the star is contracted. So what we get here is, what we're looking for in part C is what's the distance traveled according to the observers on the spacecraft. So like we talked about yesterday, if you're traveling at the same speed as someone perceives on Earth, but you're taking less time, then you also perceive less distance to be traveled. So for part C, we're using a length contraction, and we're using 10.6 light years for L naught. Because remember, that's how far that an Earth person would measure you to travel. So according to you, you only go 2.97 light years. And finally, part D is asking, what will the spacecraft occupants compute their speed to be from the results of B and C? So what we're basically doing is making sure that the delta T naught and the L make sense. So we're hoping to get we would hope that if we do the division, L divided by delta T naught, that we would, where's the 2.09 years come from? Not sure where they got that. Sorry, yeah, this is delta T naught. Yeah, this is right, this is right. I looked at the light years and I thought that was delta T naught. See, years and light years, that gets confusing sometimes. Okay, yeah, so this is your delta T naught, and this is your distance in light years. So when you divide light years by years, what you get is basically a velocity in terms of c. So what this basically showing is that when you take the answers to B and C, you get your original velocity back, which you would expect. Okay, any questions on number 7 or number 12? Those are the two topics we actually talked about. Okay, now before we talk about 16 and 28, I'll just quickly show us what's going on with those two things. So we're going to take a quick look at the textbook, and we're going to start on page, I think, 742. Chi by Susha R. Huh?
Yes.
Susha R. Okay. Chi by Susha R. Okay.
Good.
Yeah, well, I know those numbers really well. I got to learn my thousands and my 10,000s more. Here we go. All right, so I want to slide this over here. There we go. Okay. All right, so classically speaking, what we're used to is to the idea of linear momentum, P equals mv, right? Now, as it turns out, this quantity, simply based on the fact that we have this relativistic velocity, so basically, now that we have a relativistic velocity, we can change this velocity to a relativistic one instead of a rest, a smaller velocity. So what we really get is that, we have a formula from before for delta t and delta t naught. So what we can do is we have this gamma factor we talked about. We have this thing, this 1 over 1 minus v squared over c squared. This comes up very, very often in relativistic equations, including this one. So what basically happens is at very, very low speeds, this term is basically invisible. So you're basically dividing m naught v by something that's very, very close to 1, maybe like 0.99999 something. So at very low speeds, we basically we find this to be mostly accurate. And usually our sources of error are usually bigger than whatever difference this little term might provide. But as you get to higher velocities, what we find is that the momentum actually increases. Because as you're dividing by a smaller and smaller number, this value here gets, so as this denominator gets smaller, this whole value of the momentum gets larger. As it turns out, if you were to try to accelerate something with mass to the speed of light, it would require, you basically have an infinite amount of momentum. And as you'll find later, it would basically require an infinite amount of energy to accelerate yourself to the speed of light, which is basically why it's impossible. So you're either already moving at the speed of light, or you're not. So now light itself can slow down in different mediums. That's true, but you can't raise yourself to the speed of light. That's basically not possible. Although part of our experiment today, part of our activity will involve something like that, where one of you will end up traveling at the speed of light, and you have to figure out what that means. All right, so basically, so we've got a couple of equations here for relativistic momentum and mass. So this is the mass equation. The momentum equation, and what we basically have is this p here. This p is actually equal to m relative times v, which is equal to all that, equal to m naught v over 1 minus v squared over c squared. So if you want to compare just the rest mass versus the relativistic mass, you would divide this equation by the velocity. All right, so that's where this equation comes from. So you have two equations here, one for momentum, and then a similar one for relativistic mass, which gives us an idea of how mass can increase with velocity. So when you're using work to increase momentum or increase kinetic energy, you're actually adding mass to it in addition to increasing its velocity. All right, now from these equations, we also get some kind of mass-energy relationship. This is our all-famous E equals mc squared. And we'll see if we can, hold on, where's my arrow? Can't find my arrow. Oh, there it is. It's at the bottom of the screen. Okay. So I'm going to go down a couple pages here. Here we go. So now we're at on page 744, I think. Yeah, 744. And unfortunately, they don't directly derive this equation that Einstein came up with for us. But basically, this is another way of writing kinetic energy. So rather than just saying k equals 1/2 mv squared, what actually happens is it's a difference between a rest energy and a relativistic energy. So, I mean, theoretically speaking, if you had a very small velocity here, this difference in mass should be equal to whatever kinetic energy you had. Like if we're moving at 10 meters per second, you plug 10 into here, and then you get a slightly bigger value for this than this, and that difference will be equal to your kinetic energy. So this is really the true version of the kinetic energy equation that's true for any velocity up to the speed of light. So now, again, we have this gamma factor here. So basically, this is the rest energy. This is the relativistic energy that you would have at some non-zero velocity. Now, you have this gamma term, 1 over squared or 1 minus b squared over c squared. So you could rewrite this if you wanted to in a different form. You can just say Ke is gamma m naught c squared minus m naught c squared, which is also gamma minus 1 times m naught c squared. So a few different ways you can write it. But what we eventually get to is we get to this familiar equation here, E naught equals m naught c squared. Now, you're used to seeing it as E equals mc squared, but they're not telling you the full truth. This is E equals mc squared is just the popular media expression of it. But truly it's supposed to be E naught equals m naught c squared. So it's your rest energy. If you have some non-zero, if you have a non-rest energy, then it would actually be something like this. E is m naught c squared plus Ke. So all those people that have those fancy shirts say, oh, haha, Einstein equals mc squared. Well, it should really say this. Right? So now you know the real story behind E equals mc squared. All right. Now let's take a quick look again at these other two problems. So, all right, I'm going to go ahead and bring the textbook back over to my view. Okay, where are we? Here we go. Okay, so first we have number 16. Number 16 asks, at what speed will an object's relativistic mass be twice its rest mass? This one's not too bad. You're basically just taking your rest mass equation and you're plugging in 2 m naught for your relativistic mass. And then, as you probably could guess, the m naughts cancel out, and you're basically solving for the velocity. So you should get velocity there of 0.86 c. Okay, and finally, we have number 28. This one's a little longer, but I'll do my best to explain it to you here. So what we're trying to find in number 28 is they ask if you're trying to accelerate a proton from rest up to 0.997 c, how much work would it take? Well, you can define work as a change in kinetic energy. So basically it means that if it's from rest, then your rest energy would be m naught c squared, and your final energy would be m times c squared, where m is this right here. M is basically some expression of the rest mass. So when you plug, so I kind of drew an arrow here. If you plug this formula into here, you get something like this. We get m naught c squared. So if you factor out, once you plug this into here, you get an m naught you can factor out. So you get m naught c squared times your gamma term minus 1. The 1 comes from here, because you factor out m naught. Does that make sense?
Yes.
Okay. So the m naught was here, and then you had an m naught up here, and you pull both of them out. So, and what you're looking for is, you're looking for the work done. So you're basically just plugging all your numbers into this part here. Now, here they used the rest energy of the proton in mega electric volts, but you could have just as easily used the rest mass of a proton in kilograms. So your final answer could have either been 11.2 times 10 to the third mega electric volts, or you could have had 2.23 times 10 to the negative 9th joules for that one. All right, in part B is asking what would be the momentum of this proton. So now we're using our relativistic momentum equation. So again, this is the rest mass of a proton that we're using. Here's our speed of light. Not speed of light. Here's our velocity of the proton itself, and then here's our speed of light, and then here's our gamma term down here. And so what we get here is our momentum is 6.46 times 10 to the negative 18th Jordans. There you go. Probably the first time we talked about momentum this year, so now we get to use our new unit. All right. Any questions on 16 or 28? I know those were kind of new topics, so I just wanted to clear up any confusion that might have been. Okay, here's what we're going to try next. We got about just over 15 minutes. Hopefully we can get this done quickly. We'll try to. But here's the general idea. We're going to imagine that you all had your own spaceship, right? A spaceship that's capable of traveling at relativistic speeds. And so, according to Earth time, you've been gone for 60 years. But you're all going to the same destination, and you all come back in your own little spaceships. Then you land, but then somehow you never really kept track of how long you were in space from your reference frame. So you're like, oh snap! I forgot to log in the computer. I forgot to keep time, right? Maybe you're sleeping half the time and you just kind of lost track. I mean, you don't really know what day it is anymore. So But what you do have is, you know how fast you were going. So you'll get a sheet that has some kind of velocity on it. And also, before you left, one of your friends was really excited about it, and they said, "Oh, I'm traveling at this speed, and based on that, my calculations, when I get back, I'll be this old." So you have your velocity, and you'll be given someone else's age. Yep. So someone will be trying to find that age. Your friend will be trying to find you, while you will be trying to find who has based on your velocity. You're going to want to figure out, first of all, how long has it been for you. So I'm giving you a velocity here. Your delta t is 60 years. You have to find your own delta t naught. All right. Now, I'll try to give you a hint maybe 5 minutes in to speed things along, but someone in the room will be the youngest of all the travelers. And then someone else in the room will be the oldest of all the travelers. So the most important piece of information will be the youngest person. Because then you'll be able to know, based on your delta T naught, how old really are you right now. Because you'll know your change in time, but you won't know how old you were when you left. So see if you can find that person. Let's see, I could use a few helpers. Let's see, Paul, can you help me pass out, can we pass out some speeds to your side of the room here? Okay. And Jason, can you pass the speeds to this side? Alright, and then let's see, one more helper. Aaron, can you help me pass some ages to this side? Each person gets one age.
Okay, so let me do this way. So we're all on the space ship.
Different spaceships, yes.
All of us are just going into space. And this is the age when we get back to
This is someone else's age when they got back. It's our friend's age. So they don't match. They're mixed and matched. Does that make sense? So it's your speed, but someone else's age.
But someone else is on Earth or traveling.
Or someone else's Earth age.
60 years is Earth year.
Yeah, 60 Earth years was the, that was the Earth years. Who's missing an age? Here. All right. Does everyone else have an age and a speed? Does everyone have what they need? Yes. Okay. Maybe I have someone missing or something like that. All right. Does everybody have a speed and an age? Just one speed, just one age. Everybody check.
So we're covered at our age.
Yeah.
So at what age do we start?
So that's what you got to figure out.
How old am I when I get back? We don't know. How old am I when I left?
That's what you're trying to find.
I don't even know how old my friend was when I left.
You know this? Yes. Oh, the 2 ages? Okay. That's probably why. All right, here you go. All right. So now I have an age and a speed too. Ready? Okay. Then I'm gonna play too. All right. So Atticus, what was your question again? Sorry.
Can you demonstrate how you're gonna do this? At least, yeah.
Okay, I can try. So basically, I've got a speed of 0.2604 feet. Okay. And I have an age of 46. So I've got a friend somewhere in the room that's got an age of 46. Now, I don't necessarily need to chase that person down. I just have to keep in mind that someone might come up to me and say, "Hey, do you have 46? Now, for me, my speed is 0.25604 C. I've got to calculate, okay, based on this, what's my delta T naught? How long was I gone according to my reference frame? Does that make sense? So that's your first step. And then from there, you can start going around the room and seeing what ages other people have, and hopefully, eventually, you'll be able to find you'll be able to see who has the lowest age. And I'll tell you in a few minutes, because we're actually running a little low on time. So I'll try to save a little bit of time, but I'll give you a couple minutes to, so the first thing I want to do is use your speed, find your delta T naught.
Already done.
Already done. And then after that, you want to go and see what ages other people have. What would yeah? Delta T is 60 years.
Excuse me, Gordon.
Yes.
What if my speed is 0 C?
Well, that's a good question. What is 0 C? What does that mean? What do you think were the implications of that? It means what does it mean about how is 0 age compared to everyone else's? Yeah, you need it over.
Okay.
So now you want to look for whoever has the highest age. So your job's a little easy. You don't have to calculate your speed, but then you have to go around and see who has the highest age. Okay. That's your job, Kevin.
Okay.我过了48年。我有87，有人比20岁更年轻了吗？这样。所以他想的意思是80。Wait, Jordan. Say Jordan, why does he say 20 years and I say 18? What's a year mean? Oh,
I don't know why I put years on that one and I'm So it means that you're the youngest who's the oldest. Oh no, you're the youngest and he has the oldest age.
80.
Yeah, it means that somebody's 80. Somebody in this room is 80 years old.
I must be funny. So 4 years has for you. No.我真的很想有个标准嘛，因为有一个人进入我下边，然后早就了，然后早就吧，因为我也看完了。我虽然我看了48年，最后我现在16，我大概知道了。但是你们让我想那个跟我这个走的时间是一样啊，对，你现在知道你现在。啊，我现在这个是啊，这个是他的哦。是在这个时候上。他现在还不知道我这是一突然我一下我有点都低，我就不知道在，你知道吗？就是不知道。有这样子说，我拿28，哎呦，我这样还是一个我拿了有人拿了28，完美。那我了。Wait, Jordan, isn't it you our best friend that's our best? Yes. So what if he got 40 years? So he has a friend is 40 years old now. I forgot that. No, he can't be that. So how could I have a friend? All at the same age. You're all adults when you left. Right? We left all. Well, you don't know. Someone here is the youngest age. Okay. Does anyone have anything less than 20? I told you.
I calculated my pregnancy model and I got 18.
18 years. Okay, but that doesn't mean that you're, but so 18 years plus however old were when you left, right?
I know.
So what I'm asking is, does anyone have an age that's less than 20 on this? No. So 20 is the youngest here. So whatever delta T naught you get, add 20. That's what you're looking for. Okay. So now you know the minimum age, so add the two together. That's how you find your current age.
Now yours, I think it was
Okay, I've got 46. Who's 46 years old? Where's my friend? Looking for my long lost years old. You go to Florida. We're just about running out of time here. I wish we'd have had more time for this. But
what I'm going to do now is I'm going to show you what you should expect to get. All right. So part of what I wanted to do this activity is just to give you an idea of just how fast you have to move in order to get a significant time difference. So take a look at the age that you had, and see how the speed compares. Some of you might have already mastered that. Maybe some of you didn't get a chance yet. But what you can look at, first thing we want to look at is the two key ones: the oldest and the youngest. The oldest. Who was the oldest? Kevin's the grandpa. he's the So basically, he didn't go anywhere. His engines couldn't work, so he was kind of stuck.
And then we can also sing the year.
Yes.
Why you guys stay in a special didn't move?
I don't know, maybe because you didn't have a re-entry capsule and it took you 60 years to fix it.
Okay.
We'll go with that. Okay, now, here's the other one. Someone else was 20 years old. Who was 20 years old? Who was 20 years old? Was it Richard?
No. He's 28.
Okay, who was 20? Oh, that was you, Alice, right?
But I calculate the wrong because my number is 60.
No, that's right. That's right. I mean, that means that for you it was 60 years that you were gone, right? No, that can't be right. Basically, when you're traveling at 1.0 C, that means that your delta T naught is basically, I think it ends up being infinity, because you're divided by 0. So what that basically means is you don't experience a passage of time for your you don't experience a passage of time when you're traveling at light speed. So Alice didn't age at all. She was traveling at light speed, which is technically impossible, but I just use this as an example. But as you can see here, once you start to get above 90% the speed of light, what happens is if you want a 2-year increment, like 42 to 40, 40 to 38, the speed increments are much smaller as you get here, right? It's kind of like an asymptote. Yes. So whereas here between 80 and 78, I had the 78, so I was still pretty old. Just to have that 2-year difference, you have to go from 0C to 25%. Wow. Right. Just for that one small 2-year difference. But then you move over here, and the only difference between, say, 24 and 22 is like 0.002 C, by contrast. Right? So as you get closer and closer to the speed of light, it doesn't take much of an increase in order to have much more relativistic change. What this also tells you is if you want to have, that when you're thinking about interstellar travel, that if you want to be able to make a journey within your same lifetime, you have to be thinking about relativistic speeds. Because if, for example, something is 600 light years away, and you're traveling at, like, say, and you're traveling at, say, this speed here, maybe for you that's only 300 light years, right? But it's still half the distance, and it's still, it's still longer than a human lifetime. Like if something was 600 years away, 600 years of travel away, then for you that distance would decrease. So the faster you go, the less distance you will travel and the less time will pass. So it kind of gives you an idea of for a certain objects, like a certain star that's a certain distance from us, how fast would you have to travel in order for it to be within one lifetime. So oftentimes when we talk about interstellar travel, it often has to happen across multiple lifetimes because it's hard to imagine physically traveling at these speeds. So that's what I wanted to try to demonstrate with this activity. I wish we had a little more time with it, but hopefully at least found it a little interesting. So that's about all we're going to cover for relativity now. So this is just about the end of chapter 26. You will have a quiz on next Tuesday. It's mostly going to focus on time dilation and interaction, not so much the energy stuff or the momentum stuff. Maybe a little bit, but very simple. Okay. So I'll give you more details on that later. Okay. Okay, last thing before you leave. I'd like to collect I could use some assistance collecting the ages and the